Okay.
Please start. Yes.
Thank you. So this is the talk about massive gravity, massive gravitons. So far, there has been only one talk about massive gravitons yesterday of Vasilisa. So maybe the subject is out of fashion. I don't know, but I'll explain in a moment what massive bigravity is. And first, for the motivation for the problem we considered. The theory of massive bigravity was invented 10 years ago in 2011 by Hassan and Rosen. And then next year, I was able to produce a paper on classification of hairy black holes in this theory. And I found generic types of black holes, but not asymptotically flat. Because asymptotically flat solutions are very special, and in order to construct them, one needs to fine-tune parameters. And for this, additional information was needed, and this I didn't have at the time. But next year, there were two papers of two groups of Portuguese group of Brita, Cardoso and Pani, and the group of Babetif and Fabry, who studied perturbation of Schwarzschild solution embedded into the theory. And they detected the phenomenon of change of stability. And the Portuguese realized that this was the information necessary in order to construct hairy solutions. And so they did it. Before they published their paper, they sent me their data. I checked them, and it was okay. And so they published asymptotically flat black holes. But surprisingly, 4 years later, there was a paper of a Swedish group coming from the same place that in Stockholm, that from the same place where the bigravity was invented. These are reasonable people, rather mathematical, and they wrote a paper devoted to analysis of mathematical structure of the theory, like coordinate system, convergence, etc., etc. And among other things, they claimed that the only asymptotically flat black hole solution in the theory is the Schwarzschild one, the trivial one. Well, I was surprised because I checked this myself and it worked. So I talked to them, and then they said, no, only Schwarzschild, nothing else. Well, and last year with my student Roman Gerval, we started looking into the paper, and we studied it carefully, and we realized that they did not have a proof. They only gave, they only formulate the statement as a conjecture, and they gave a number of plausibility arguments. And in particular, they criticized correctly certain problems with the numerical analysis, which appear in many publications. And therefore, we tried to adapt our numerical scheme in order to do everything properly. And then finally, we were able to reproduce the results of the Portuguese group. But also, we obtained many new results. In particular, we studied stability, etc., etc. And this I will explain to you now. And so the paper was published last December. Okay. So about gauss-free bigravity. This is the theory with two dynamical metrics, usually called F and G. And each metric has its own kinetic term of the standard type of Einstein-Hilbert type, R of G and R of F, and with two gravitational couplings, with two Newton couplings, if you wish, called kappa 1 and kappa 2. But in addition, the action contains the potential term describing interaction between the two metrics. And then the potential is a sum of elementary potentials with arbitrary coefficients B. And then the elementary potentials are are constructed from eigenvalues of the following matrix with a square root. So this is, and this particular construction makes sure that the dynamical degrees of freedom in this theory correspond to two gravitons, one massless graviton with two polarizations, and one massive graviton with 5 polarizations. And if these parameters B are restricted in such a way that they're expressed in terms of two parameters, usually called C3 and C4, then flat space is the solution of this theory. And then this M becomes the first Pauli mass of massive graviton. And in addition, I should say that we can also assume the coupling to a matter, but the important point that the matter is coupled only to D metric in our setting. Therefore, this is important. Therefore, the second metric is not directly visible. It's not measurable. Only G metric is seen. Okay. So when we vary the action, well, it is convenient to rescale the metrics in such a way that 1 over m becomes the length scale. And then after this rescaling, equations of motion become completely dimensionless. And where the couplings kappa are also rescaled in such a way that this kappa 1 and kappa 2 expressed in terms of a sine and cosine of a mixing angle eta. Okay, so now we have a completely dimensionless theory. So the two sets of Einstein equations are these source terms which describe interaction between two metrics f and g, and there are different terms t and t. Another t. So again, we can set the matter term to 0, and then the flat space is the solution of the theory. And if one studies perturbations around this flat space and builds the linear combination of delta f and delta g, then one discovers that the first combination fulfills linearized Einstein equations. Therefore, it describes massless graviton. And the second one fulfills first Pauli equations. And therefore, it describes massive graviton. Many solutions of these equations are known. Many cosmologies, describing cosmologies, stars, wormholes, etc., many. The simplest ones are obtained by setting the two metric to be equal to each other. In this case, the source terms here vanish, and everything boils down to usual vacuum Einstein equations. And therefore, any vacuum metric provides a solution of the theory. In particular, one can take Schwarzschild solution, and it gives the solution of bigravity equations, which we shall call Bolt-Schwarzschild. And here r is the radius is in units of 1 over m, and the mass m is expressed in these units. And important point is that even though this coincides mathematically with Schwarzschild, physical properties of this solution in bigravity are different. In particular, if one considers perturbations around this background, then due to the fact that delta G and delta F need not to be identical, even though the backgrounds are identical, the perturbation equations admit unstable solutions, growing modes, and this is important for our subject. And then one should say that the graviton mass m should not be should not be too small, because otherwise the black hole mass becomes extremely large. Next solution is this. So if you assume the two metrics to be proportional to each other with a constant coefficient, then the equations reduce to Einstein equation with the cosmological constant. And so the cosmological constant lambda can be positive or negative, depending on the choice of C, and C is not arbitrary. It's a solution of a certain algebraic equation. So therefore, de Sitter and anti-de Sitter are solutions. And in particular, de Sitter is a solution. The fact that de Sitter is a solution means that the theory contains self-accelerating solutions. So describing expanding universe with the lambda expressed in terms of graviton mass and the coupling kappa 1 in this way. And we know that this thing should be inversely proportional to the Hubble squared. And I must say that this formula is provide the whole motivation for the theories with massive gravitons. Because if we consider just lambda as lambda, then it's very difficult to explain from the quantum field theory point of view why it is so small. And this leads to the famous cosmological constant problem. Whereas if lambda is expressed in terms of m in such a way, it's much better, because from the quantum field theory point of view, it's more natural that m is small. There are arguments for this. So this is, if you will, the original and the strongest motivation for theories with massive gravitons. So this explanation of lambda. And so to agree with observation, one can assume either that m is of the order of inverse Hubble, but this is not interesting for us, and therefore we adopt another option that kappa is small. And if kappa is small, then this leads to hierarchy of scales between the two couplings. And in fact, this hierarchy is needed, as was noticed before, needed in order to remove the instability in the cosmological solution. And for this, one has to assume that kappa 1 is of the order of the square of ratio of electroweak scale divided by Planck scale, and numerically is 10 to the negative 34. So this is a very, very small number. And if we assume this, then we find that 1 over m is a reasonable thing. It's of the order of million kilometers, which is about the size of solar size. And even though expressing in electron volts, it seems to contradict the observational bound, but I will explain this. So again, we assume m to be 1 over m to be of the order of solar size. And next, how we construct these solutions. So we assume the two metrics to be static and spherically symmetric. And then the G metric is assumed to be in the Schwarzschild gauge. Therefore, here R squared is in front of the line element. Whereas for the F metric, there is another function, arbitrary function. And if we require G metric to be a black hole type, therefore we require Q squared and N squared to vanish at some point. Then we discover that Q squared and Y squared must vanish at the same point, otherwise everything is not compatible with the equations of motion. And therefore the horizon must be common for both metrics. In other words, horizon is the the hypersurface, which is now with respect to each metric. And the surface gravity and the temperature are also the same. However, the horizon radius measured by G metric can be different from the horizon radius measured by the F metric. And then the independent field equations reduced to three independent, with very complicated functions on the right. But what is important is that for a given value of even horizon, the value of this function at the horizon, sorry, of this one at the horizon, completely characterizes the boundary conditions. And therefore, one can do the following. One can fix RH, one can fix this number, and then simply integrate these equations forward to see what happens at infinity. And this I did originally, and what happens is this. As one approaches infinity, one discovers that either solutions approach ADS or they become singular. But one never finds asymptotically flat solutions. One can try many different random choices of these two parameters, and one never finds asymptotically flat. And this was my observation, and also the Swedish, they confirmed independently the same thing. And the reason for this is the following. If you linearize the equations around a flat space at infinity, then the solution is roughly has the following structure. There is a decaying Newtonian tail owing to the massless graviton. There is a decaying Yukawa term due to massive graviton, but there is also the growing term, exponential growing term, and this term spoils everything. So it is generically present in the solution, and it doesn't allow the solution to approach flat space unless one suppresses it from the very beginning. So in principle, one can do this. One can just set C to 0, and then one can integrate the equations from both sides, from horizon towards infinity, and from infinity towards horizon, assuming only these two pieces, and then do the matching in between. But the problem is that this requires a fine-tuning, because one has to know where to start. One has to know one has to give some input parameters, some input values for these three parameters, but without extra information, no hope. And this extra information was obtained in the analysis of stability of Schwarzschild. So again, the ball Schwarzschild is this, and if one studies perturbations around, and if the time dependence is a harmonic one, it turns out that the perturbation equations boil down to a linear eigenvalue problem with omega squared as eigenvalue, and there are bound states with negative omega squared, but these bound states exist only for small black holes if the RH is less than certain critical value. So therefore, there is a change of stability. And this was discovered independently by the Portuguese group and also in the paper of Babichev and Fabry. And then the Portuguese, they realized that this change of stability can be interpreted as a bifurcation with a new solution. Because if RH is equal to exactly 0.86, then the perturbation equations admit a negative mode, which means a static, normalizable solution, which can be considered as a perturbative approximation of a new static solution which bifurcates with Schwarzschild. And these facts give the correct input values for the numerical procedure. And Babbage and Fabry realized that this eigenvalue problem is mathematically precisely equivalent to the problem studied by Gregory and Laflamme in the analysis of the stability of black strings in 5 dimensions. And so therefore, we call this particular point Gregory-Laflamme point. And so one has to start numerics at this point, and then we deviate from this point. This gives sort of fully fledged black holes. And numerically, it's a bit tricky. It's not completely obvious. So mathematically, one has to solve for nonlinear boundary value problem. Because one has to integrate the equations between 2 singular points, horizon and infinity. And in order to do everything properly, we did a desingularization of the equation at the horizon in order to be able to start integration exactly at RH and not outside and not the epsilon distance. Then at infinity, at large R, we converted everything to the equivalent set of integral equations, and then we solved them by iterations. And then in the intermediate zone between the horizon and this R maximal, we did the multiple shooting. Well, this is doable, but a bit time consuming. And here are the results. So of course, first of all, we checked the Portuguese results. They are okay. And here are some profiles. So these profiles, these are amplitudes of the hairy solutions divided by amplitudes by the Schwarzschild amplitudes. So these are ratios. And these ratios approach unity far away. Therefore, asymptotically, the solutions they become Schwarzschild. Whereas in the vicinity of the black hole horizon, there is a deviation from unity, and so this is the region where, if you see if you will, massive graviton hair is located. And one can change the theory parameters C3, C4, eta, and the event horizon, and then one gets different solutions. And one should say that solutions do not always exist, not for arbitrary values of parameters, and it requires some work to construct them. And then the property particularly useful is the duality that we used, because the original theory is invariant under the following substitution, under the following replacement, and this allows one to relate 2 different solutions to each other. So if there is a black hole for certain values of theory parameters and for certain event horizon size, then for dual set of parameters, and then for dual size, there is another solution for sure. What is important for us is it's called Harry-Schwarzschild. So these are our equations, and the parameter kappa 1 is extremely small, very, very small. And so if it is exactly 0, then the G metric becomes Schwarzschild, whereas F metric is not Schwarzschild. It's a hairy metric which contains hair, and so this we called hairy Schwarzschild, and these are solutions which approximate well the solutions for this value of kappa. Well, next, stability. This is the whole issue. So we considered only a sector So first, we assumed the both metrics to be spherically symmetric, but time dependent. Then G metric can be put into the Schwarzschild form, diagonal form. But if you assume this gauge, then the second metric is in general not diagonal. It contains off-diagonal element. And so if we, when we expand everything around static background, static hairy background, then after, well, assuming harmonic time dependence, after many hairy transformations, everything boils down to a single Schrödinger equation. So I emphasize single. There were, in this conference, there were some talks about Reggie Wheeler and two parities. No, there is only one parity. So this S sector, massless graviton is non-dynamical in this case. So only the massive one, which describes the scalar polarization of graviton, so it's a scalar, essentially a scalar field. But the scalar field is parity even. So therefore, we have a single one-channel Schrödinger equation with a rather complicated potential. And then skipping all the details, we were able to find solutions with bound states and without bound states, so stable and unstable. All solutions previously discovered by the Portuguese group are unfortunately unstable, all of them. And this creates a puzzle because it's completely unclear what they decay to. So they are more energetic than Schwarzschild. And then the first idea is that they decay into Schwarzschild. But the Schwarzschild is also unstable. So therefore, it's unclear what happens when the instability grows. However, the nice thing is that hairy black holes are stable if kappa 1 becomes very small, and this is was great news for us. And so this is the general description of solutions. Solutions depend on 4 parameters, and it's difficult to carry out a complete classification. But the idea was to use to represent some pair of values for this C3 and C4, and then the described solutions as the functions of RH and kappa. And here is the important thing. This is the mass. This is the mass of solutions, ADM mass, against the event horizon size for different values of kappa. So all solutions pass through the Gregory-Laflamme point where they bifurcate with the Ball-Schwarzschild. Then they deviate from Ball-Schwarzschild as one deviates from this point. And only if kappa is 0, then the G metric remains Schwarzschild, whereas F metric is different. And for other values of kappa, everything is no longer Schwarzschild. And what is interesting, we see that the mass is more or less for all solutions, more or less the same as for the Ball-Schwarzschild. And this is the mass of a Schwarzschild black hole of size 1/m. And therefore, we cannot assume 1/m to be of the order of Hubble parameter of our universe, because this would give us ridiculously large black holes. Instead, we assume that 1/m is of the order of solar size, and then our black holes have typical mass, maximal mass actually of the order of million solar masses, which is fine for typical supermassive black holes. Next, we can split the mass into the horizon contribution and then the hair contribution. And then, oops, sorry, something went wrong. Something went wrong. Okay. And then we see that on the left from the Gregory-Laflamme point, the hair mass is positive because the solutions are more energetic than Schwarzschild. Whereas on the right, the hair mass is negative because the effective energy is not positive definite. And then the interesting question is what happens in the limit. So when RH approaches 0, then the geometric approaches a singular, the mass remains finite. Therefore, everything is contained now in the hair. And so the geometric becomes singular, whereas the F metric remains regular, and it remains of the black hole type. In the opposite limit, it's interesting that solutions disappear during the so-called fusion of roots. And then in the vicinity of this right boundary, the effective graviton mass becomes imaginary. So the gravitons behave as tachyons. And here is the parameter space. So here on this axis is RH, and then on the vertical axis is eta, therefore kappa 1. And so the solutions exist within the finite domain. So the lower boundary is a boundary where F metric is Schwarzschild. On the upper boundary, G metric is Schwarzschild, and most importantly, these dashed lines show the boundary of the region where stability changes. Therefore, omega squared is positive here, so therefore all this region is stable. So the solutions are stable, and then the physical solutions correspond to this line, so that they're extremely close to the upper line. And again, for these solutions, kappa 1 is very small, so the physical geometric is extremely close to Schwarzschild, and all the hair is contained in the F metric, which is not directly visible, it's not directly measurable. And therefore, these black holes normally cannot be distinguished from Schwarzschild unless in violent processes like black hole collisions. In the collisions, this T-menu effective becomes strong enough in order to overcome this suppression, and then we expect that the signal from these collisions should contain some imprint of the hair. And then we tried to somehow evaluate this T-menu for very small values of kappa. And when we, in particular, we obtained the following estimate, and we discovered that this interaction between the two metric becomes larger and larger when the black holes become smaller and smaller. So therefore, the hairy features are expected to be more pronounced in small black holes. And I think I am running out of time, so let me just come to my summary. So here are our results. So we confirmed that the theory admits stationary and asymptotically flat solutions with discrete black hole with massive hair. So we assume the graviton mass to be of the order of solar size, for the black holes not to be ridiculously heavy. And then the agreement with cosmology is achieved if kappa 1 is this number. And stable black holes are described by geometric which is extremely close to Schwarzschild, but their F metric is different. And their masses range from roughly 0.2 solar masses till million solar masses. So if by gravity indeed describes physics, therefore, in this case, the conclusion is that real black holes cannot be pure Schwarzschild. They must hide inside hairy features. So the F metric is not, which contains hairy features, is not directly measurable, and therefore, in usual situation for usual unperturbed black holes, the hair is not visible. However, in black hole collisions, the interactions increases, and therefore the hair should become, or may become, or may become visible. And this presumably can be detected in the LIGO observations. And then the effect should be larger for small black holes, because for small black holes, this T mu increases. And therefore, one can say that maybe so far nobody have seen hairy features simply because the black holes measured are too heavy. So yesterday we saw a talk. There was a talk which mentioned the lower boundary of 5 solar masses. Presumably, one has to descend, and then we shall see so when signals from small black holes are detected, maybe we shall see something. Thank you. That's it. Yeah. Thank you.
Okay, thank you very much. Any question and comment? Yes, so please, Chae-Yun Cheng.
Yes, I have a quick question. So you say that in this model we can only see the G metric because it is the one that coupled the matter.
Yes.
So is it possible to have a solution, a black hole solution that is stable in G metric but is unstable for F metric? If yes, is it physical?
No. The stability includes both metrics. So the stability essentially, so in the stability analysis, one should picture both of them. And
yes.
So either both of them are stable or both of them are unstable.
Oh, okay.
If they're both stable, then G metric is visible, F metric is not, but they're both stable. Yes.
Okay, thanks.
Okay, Alexander, please.
Okay, do you hear me?
Yes.
Yes.
Yes. If I understood you properly, you showed that your low limit for hair black hole is smaller than Oppenheimer-Volkov limit. In this case, is it correct or not? Because low limit for hair black holes.
Yes. But
in this case, if people will discover such kind of black holes, they cannot be a result of, let us say, probably standard evolution. It's something like signature for this kind of phenomenon, or primordial black holes. What about this issue?
Yeah, I think there should be a kind of primordial black holes. Of course, it's not Oppenheimer-Volkov, something else. So some black holes produced by density fluctuations or whatever. Yeah,
okay,
something this kind. Yeah.
Okay, thank you very much, Mikhail. So let's move on to the last talk.